So in this course, we have to try to do an introduction to the field of optimization, and in particular, the optimization of QO products. Okay, so in the first lectures, we basically tried to motivate that the QO family of optimization problems was an interesting family, and we have shown examples of how practical problems can be mapped into a QO. Okay. So in the queues, we have proposed strategies to solve these optimization problems, and we started for the classical strategy, so classical algorithms, also quantum analog, and quantum digital. So basically, the challenges in the future of optimization, in order so the goal, what we would like to have is to reach the quantum advantage in which the hardware is mature enough, is good enough to produce these polynomials speed up compared to the classical algorithm. So far, no quantum advantage has been shown yet, and the main challenges that we have in the future is, on the one side, is to improve the hardware, right? So maybe the quantum analog would need is to increase the coherence times, and also another important feature for the annealing is that so another important feature for the annealing is that the connectivity between the chips increases, so that we can interact any qubit with any other qubit. Okay, so that the topology of a chip usually has a limited connectivity to the connections that you have in your chip, and then what you have to do in practice is to use the idea of physical qubits and logical qubits. So in practice, in the future, we will have many more logical qubits many more physical qubits than logical qubits. And the idea is that in your abstract logical space, you will have arbitrary connectivities. So any qubit could be connected to any other qubit, but this will be implemented in a low level of hardware by means of some intermediate qubits that will enable these interactions. Okay, so one other challenge, let's say, is the increase the connectivity of this. Increase the connectivity. Okay, concerning the quantum digital, there is room for improvements in the fidelity of the data we get, both for the gates and the readouts. Okay, so the idea would be increase the fidelities of both gates and measurements. Okay. Of course, there is an ideal, that is that we also increase the number of qubits. Although I would say that nowadays the main limitation to get a quantum speed up, to show this quantum advantage, is not the number of qubits, but more the quality of the qubits that we already have. So with the same number of qubits, because of both D-Wave and IBM have chips with thousands of qubits or with 1,000 qubits, and if we had high coherence qubits with low noise, we should be able to show a quantum speed up. Remember that even the whole, so even if we use the whole universe, the whole observed universe, to encode a quantum state, and we use every atom of the universe to encode one bit of this quantum state, so we wouldn't be able to represent a quantum state of more than 358 qubits or something of this order of magnitude. So clearly, the problem now is not about having not enough qubits, but having a higher quality qubits. Okay. If the goal is to show quantum advantage, there is another thing that will be very important. So we will need, so it's possible that the typical arguments in the scaling of the complexity of how the number of steps of the algorithm scales in complexity with the system size, with the size of the input of the problem. So this type of arguments, it's possible that they no longer apply because the coefficients matter a lot. Okay, and it's a good field of research for this will be the computational benchmarks. So we need to reach a consensus on certain problems that are very hard for classical methods, and but basically in which classical methods are stuck, and where we can show that our quantum alternatives really are able to make it better than the classical methods. Okay, so there is a field that it will be very relevant in the future of proposing problems that it's not that we want to solve these problems in particular, but that we want to see these problems as problems where classical methods get stuck, and we can show that we achieve this quantum supremacy. Another field that will require a lot of attention and focus in the future will be in the theory, in the development of new algorithms. Okay, so we have presented here a series of algorithms, but there is space for many new ideas. And here, some effort should be done also by the scientific community. Finally, I think that it's nice to mention that we are entering in a kind of nice era where the best things are yet to come. And it's when we combine all these ideas that we have said, no, that optimization, if you want quantum, optimization, quantum, that we have seen how they interplay, how they interact. So the optimization problems are useful in the development of quantum technologies. They also, the classical optimizers are used in some hybrid methods. No? So we see that here there is a strong interaction of how quantum algorithms can solve optimization problems. We see interactions here. But there is another field that we didn't mention so far, and we believe that it will be crucial in the future. That is the field of machine learning. So we really expect that the interaction between these fields will be very fruitful. For instance, in this side here of the interaction between the quantum world and machine learning, we have the field of quantum machine learning, where we expect very nice things to come. And one interesting application could be the sustainability in the sense that training these machine learning models and these language models of machine learning requires a huge energy consumption, and maybe making some of these parts quantum, we can decrease a lot of the consumption of energy. Okay. Also, machine learning can be a very good tool to develop quantum technologies. Like it can help us to make some procedures of calibration, characterization of chips, manufacturing. So make help in this task. So it can be a very good tool to develop quantum technologies. And also, it's well known the relation, the connection between machine learning and optimization, since machine learning can be used in some of the different processes, and also, of course, optimization is applied when we want to train any machine learning model. You need some optimization process in order to find the optimal parameters. Okay, so yeah, the idea was here just to do a first introduction to present the basic concepts on optimization and quantum optimization. And also, we would like to explain that the best things are yet to come because of the interaction of these two fields of the optimization, machine learning, and quantum. Let's say technology in general will lead to a very interesting future. Thank you very much for your attention.